All right. So one question from Srinivas. It says that for a general, it has a general question for. He has a general question whether Proton hierarchical handles bump placement and routing.
Okay. Short answer is not yet.
Not yet. Okay.
Yeah. We have like a non-proton tool, and we have not had chance yet to integrate it. So for now, we'll say it is not there. In case we need to, for somebody, we can enable like a separate tool for that.
All right. One question: if we have any macros or pre-placed cells, how can we include them in the chip, and how can we use decoupling capacitors for that macros? So this is a question from Praneeth. So I think hierarchical webinar might answer this particular question right now.
That is true.
Yeah. So Praneeth, right now this is a block that we are drawing, which is the macros and the pre-placed cells. Once we use this and place it on the top level and we show it, that time I think we would be able to answer this query. It will make more sense over there. So Balaji, do you share all the chat questions and answers later? Yeah, Balaji will be sharing all of them. So Srinivas has a question: how is CTS done in synthesis without flop placement information? So the way it works is basically there is a bleaf fan-out tool inside Qflow, which is again an open source, and that does the clock tree synthesis. Although there are various planned enhancements, such as there are not much planned enhancements like identifying buffers in the standard cell set, specifically marking it as clock buffers or so on. But it's a very different thing. So moreover, belief fan-out works in conjunction with the grayful placement that we saw, and it will create an input to the gray wolf with all the clock buffers which is marked as permutable. So whenever we do a simulated annealing about the placement algorithm, it causes the clock tree to organize itself into a much balanced hierarchy of clusters across the layout, which is not perfectly as H tree, but it is very close to H tree. So once the synthesis step does a limited amount of clock tree, the clock cells are again rearranged in a fashion wherever the flops are present in the gray wolf placer.
Sir, one more thing I have. People often say that if you are applying the NDR rules before the placement itself, if you are informing the tool before the placement itself, then the tool will better understand about the placement of cells, so it will be good. But how exactly the tool will come to know about these NDR rules before the placement? Where exactly you specify those things?
If I can take that question,
Yeah.
I think that NDR mostly refers to clock tree.
Yes.
And so the idea behind that is when you're placing your flops, you want to make sure that your clock pin is accessible by a wide wire.
Okay.
So when we apply the NDR and it is trying to compute the congestion, the tool is trying to compute the congestion, it can make sure that your clock nets are, or that congestion is computed with that wide wire assumed for the clock net.
Okay.
It basically ensures that once the clock tree will be done, you will have enough routing resource.
Correct.
An example would be it will not place clock pin very close to the power route or power strap, so that you have enough access with a wide wire to connect to that clock pin.
Okay. So,
Question coming up from Srinivas is: how about scan insertion in synthesis and scan reordering during placement? Do we do that yet?
I have not tried any of the scan stuff right now.
All right. One more question: if you have an IO placement, how do you place pins in this case? First pin placement and then place cell. So Sachita will answer that at the end of this particular webinar. We'll show it actually. We'll show how do we do it. And Ganesh has a question on: can you brief on placement algorithm min cut? So that's what Rajiv has already done it. Can you more or less. One more question by Rahul is: are we considering any placement constraints? So that's what again you have already answered this question. So yeah, more or less we have all the questions answered. So we'll look into the routing, and then maybe we'll take up some more questions, and then towards the last half an hour we'll take all of the questions from everyone. Yeah. Okay. Sure. I'll take up the control from here. So next is basically once we have done with the once you're done with the optimized placement and the placement stage, the next is the hyphen out net. Ideally, the next step should be hyphen out net synthesis and the clock tree synthesis. But the way the EOSys tool worked is it's already it is so if you saw the button over here, that was called as QFlow EOSys. So QFlow EOSys takes care of the hyphen out net synthesis already in the synthesis step, and it also takes care of the clock tree synthesis, which is the buffering part. This things has already been taken care at the synthesis stage, and as I just explained, based on the placement algorithm, it basically marks those. It basically rearranges the clock cells in a proper fashion depending upon which flop is getting placed at what locations of the core. So that's what it does. It's a bit different than the regular flow, but it works for small designs and for higher nodes like 110 nanometer. And then the reason we do clock tree synthesis, just to clarify, so that we are all on the same page. Basically, if you see a signal coming at the input of the port, something like this, the output, you also expect the same signal to be reaching at the 4 endpoints of the flop, but that's not the case because of the huge RC delay of the wire itself. As a result of that, we do a buffering, which is space based buffering. So at every L/4 distance, we add one buffer. Roughly, this is the distance that we see. So it might not be exact L/4, but somewhere around this number. So at every L/4 we add a buffer, and that makes sure that the signal which is being coming at the input, that reaches at the each and every endpoint of the flop, the same signal reaches at the endpoint of the flop. That's the idea. And for a clock tree specifically, there are a couple of observations over here. It has got 2 level of buffering over here. So the level of buffering are really important. And at every level, at every node, we expect each of the buffer to drive the same load in order to balance the skew from this point to this point and this point to this point. So we want every level to drive the same load, and we want identical buffers at each and every level. So this kind of sophisticated clock tree synthesis is not yet completely enabled, but it's already there in the some of them is already there in the QFlow EOSys synthesis that we have done. And finally the output will look something like this. So this is the chip, this is the place where your clock comes, and this is how the clock tree will look like. So let's look into a small. So this is how your clock tree will look like. The yellow line is the one, it is the clock input, which hits 4 clock buffers, and each of the clock buffer go to the respective flop placement. So this buffer, the blue lines, is the output of the clock buffer that goes to each and every cells which is placed on this particular core. So Rajiv, now I think it's the right time to show them the fly lines of the clock tree. Let's show the clock tree fly lines.
Okay, sure.
And then we'll do the routing, and we'll take up some more questions after routing.
Okay. So to browse the design, actually, let me switch off the power nets just so that it makes it easier to see. So there are a couple of ways to see the fly line. One way is you press the L button and draw a box around any of the instance. So it will show you its connectivity. So basically, blue pin is the output, and the yellow is the input to this cell, yellow net. So there are basically, looks like this has 2 nets or something connected. So this is a way to analyze fly line in this thing. So you can enable fly line here. Another way to do this is go to design, and then you do query. And let's just pick up the clock net here. So CLK. And then you can do it in the netlist mode because it is not routed right now. So we just do select, and you can see the clock net here. So basically, these are the 8 buffers that buffer the clock net, and then and if you want to show the fly line, we can just basically press L and draw a box around one of the instances. So we can see that the clock net comes in, gets to the 8 buffers, and then each of these 8 buffers drives another 8 flops, I think, because there are 64 flops in this design. It's a 16-bit multiplier, so 16 inputs, 16 out, 16 inputs and 32 outputs, so 64 flops in total.